Now we talk about Airy functions as we continue with the special functions playlist. And here we were looking at Airy differential equation, turning point theory, and uniform asymptotics. Okay, so um, Airy functions arise naturally in differential equations near a turning point, where the nature of the solution changes from oscillatory to exponential. All right. So, I mean, we saw something close to this when we're looking at asymptotic methods, asymptotic methods in the other video. So you see how you can have change of form from oscillatory to exponential behavior. So applications can be found in quantum mechanics, optics, wave propagation, WKB theory, asymptotic analysis, and diffraction theory. The central equation is the Airy differential equation. So it's good we see that now. So the Airy differential equation is simply d squared y dx squared minus xy equals 0. Or another way of writing it would be y prime prime equals xy. So you can remember that this is sort of close to what we saw the other time for um I think was it also called the Airy equation where we had epsilon squared y prime prime equals q of x multiplied by y, right? So it's pretty close to that. So this is the second order linear differential equation with variable coefficients. So what is the nature of the solutions you get for Airy equation differential equations? First of all, um, the behavior of solutions depends strongly on the sign of x. So the sign of x determines what happens, right? First of all, you have region 1 where x is greater than 0. So where x is greater than 0, solutions behave exponentially. And one solution grows rapidly, one solution decays rapidly. So you have growth, one solution. Then, of course, because it's a second order equation, you can expect to get two solutions at the end of the day, like y1 of x and y2 of x. So one grows rapidly, the other one decays rapidly. Then the second region is where x is less than 0. So solution becomes oscillatory when x is less than 0. So you can see how movement can happen from when x is 0, it's exponential. When x is less than 0, it is oscillatory. Thus, x equals 0 acts as a transition point between oscillatory and exponential behavior, right? So you then have power series solution to the Airy equation. Don't forget, Airy equation is y prime prime equals xy easily. So the power solution, which I dealt with thoroughly under the differential equations playlist, right? So if you assume a power series solution where y of x is summation from n equals 0 to infinity, a sub n, x raised to power n, then y prime prime of x, that's if you differentiate this twice, that will start from n equals to the first time, you have n ax, n sub a sub n raised to power x raised to power n minus 1. Second derivative now, you have summation from n equals to infinity, n into n minus 1, a sub n, x raised to power n minus 2. So if you now substitute this into the Airy equation, that's simply y prime prime that you have your minus xy equals 0. So if you shift the indices now to balance things up, so here you can have if you shift it two steps now, so it means n becomes n plus 2 while n minus 1 becomes n plus 1 because that's n minus 1 plus 2, which is n plus 1. Then you have an plus 2, then x raised to power n minus 2, so plus 2 now, that's x raised to power n. Then coming here, you shift this to 1, right? This is x multiplies this, so you have um so it's 0 here, right? So, but by the time you multiply by this, you have summation from n equals 1 to infinity. Then you have a n minus 1 x raised to power n, and that is equal to 0. So equating coefficient then gives you that, it tells you that a2 is equal to 0, right? Of course, if you take, if you substitute now, you have 2 a2, right? When n is 0, you have 2a2 x square x. Now, in fact, 2a2 in short minus here you have you know, this is a naught x raised to power 1. So a naught x raised to power 1. Or you have to shift this backwards. So in that case now, a2 is greater than or equal to 0. And for n greater than or equal to 1, you have that an plus 2 is equal to an minus 1 all over n plus 2 n plus 1 like that. So this n plus 2, n plus 1. So you have an minus 1 all over n plus 2, n plus 1. So with that in place, this recursion generates two identical solutions. So the two standard independent solutions are now AI of x and BI of x, right? So the general solution then becomes y of x equals C1 AI of x plus C2 BI of x. So then we talk about the qualitative behavior of AI of x and BI of x. So AI of x decays exponentially for x greater than 0 and it oscillates for x less than 0. Whereas B1 of x grows exponentially for x greater than 0 and oscillates for x less than 0. So you see, so the exponential behavior, whether it is growth or decay, growth decay is for a of x and growth is for bi of x. Whereas when x is greater than 0, by the way, but when x is less than 0, you have oscillation for both. So then you have integral representation of ai of x. So the Airy function ai of x has the integral representation ai of x equals 1 over pi integral from 0 to infinity cos t cube over 3 plus xt dt. This representation explains its oscillatory structure. So you can see cos that will cause some oscillation right there. Then we talk about the asymptotic behavior for large positive x. So as x approaches positive infinity, a of x is approximately 1 over 2 square root of pi x raised to power minus 1 over 4 e raised to power minus 2x raised to power 3 over 2 all over 3. Then thus ai of x decays exponentially, as you can see this minus here. Then asymptotic behavior for large negative x now. So as x approaches negative infinity, a of x is approximately 1 over root pi minus x raised by minus 1 over 4 sine 2 over 3 minus x raised by 3 over 2 plus pi over 4. Hence, you see the solution, it becomes oscillatory here. That's for ai of x. So we can take an example, estimating ai of 10, for instance. So if you use the asymptotic approximation, ai of x is approximately 1 over 2 root pi x raised by minus 1 over 4 raised by minus 2x raised by 3 over 2, all divided by 3. So for x equals 10 now, so it means anywhere you see x, you put 10. So first compute 10, this is 10, 10 raised by 3 over 2. So that is 31.6288. Then the other one now, uh you have this whole thing now. This whole thing, you have 2 here, right? So this whole thing divided by what's that? Okay, yeah, these 2 here, all over 3. So you have 2 over 3 multiplied by 31.6288. That's approximately 21.0819. So with that, we take care of this part now. And then the exponent of that, e raised by minus 21.0819, is approximately 7 times 10 raised by minus 10. So that takes care of this exponential part. So for the other part, 10 raised to minus 1 over 4, that's approximately 0.562. And then we have 1 over 2 root pi. So AI of 10 is 0.562 over 2 root pi multiplied by 7 times 10 raised to minus 10, which is extremely small because of this 10 raised to minus 10, right? And then you still have some division going on here. So it's a very simple number. So we can actually visualize that here, you know. So you have that area of x. So I have the visualization here. So you see the whole, so you see, you see, on the negative side of things, right? You can see the oscillation for both A1 of x and B1 of x. But once it crosses 1, you see B1 of x growing exponentially while A1 of x is decaying, it decays very fast and settles at 0. So according to the behavior that we have explained already. Okay, so you can see around the other time we checked around 10, right? Um, what did we computed something around 10. That's 0 point. I mean, it's very small. It's somewhere already at 0. So yeah, so this is it like that. Then we have turning point theory. Yeah, we saw this equation at the other time. Consider the differential equation exponent epsilon squared y prime prime equals q of x of y. So this looks like it looks like the Airy equation is a special case of this turning point theory or something like that. So we know that a turning point occurs where q of x naught is equal to 0. in this case. Near such a point, oscillatory solutions transition into exponential solutions. So when you cross this, then ordinary WKB approximations will fail here, and Airy functions provide the correct location description in that regard. So you can see they have a lot of resemblance. So for WKB approximation, away from turning point, the WKB approximation gives y of x, which is approximately 1 over q of x raised by 1 over 4 exponents plus or minus 1 over epsilon integral q of x dx. Now, this was the last example I did in the last video was something about Airy WKB approximation. However, this approximation breaks down near q of x equals 0, right? Because the denominator becomes singular at that point. Because q of x equals 0 here will make this whole thing undefined, right? Then we'll talk about reduction to the Airy equation. So to reduce it to the Airy equation, we then have y prime prime equals lambda squared x minus ay. So if you define a new variable now that epsilon is lambda raised by 2 over 3 into x minus a, thus then the equation becomes d squared y d epsilon squared minus epsilon y equals 0, which is exactly the Airy equation there. Okay. So with that in place, then with that, we can go ahead to talk about uniform asymptotics. Ordinary asymptotic expansions fail near turning points. All right. So Airy function approximations remain valid in oscillatory regions near the turning point and in exponential regions. This is called a uniform asymptotic approximation. So uniform area approximation then goes like this. So near a turning point, we have y of x, which is approximately c1 ai of epsilon plus c2 bi of epsilon, where epsilon is equal to 3 over 2 integral from x naught to x, square root of the absolute value of q of t dt raised by 2 over 3. So this smoothly connect the oscillatory and exponential regions like that near this turning point. So for near a turning point, that is. Then we then talk about quantum mechanical turning point. So the Schrodinger equation minus h bar squared psi prime prime plus v of x psi equals e psi, that's the Schrodinger equation. So suppose near a turning point, we now have v of x. Our v of x is approximately e plus alpha into x minus x naught. Then we say that psi prime prime is equal to alpha all over h bar squared into x minus x naught psi. And then we define epsilon to be alpha over h bar squared raised by 1 over 3 x minus x naught. So the equation becomes the Airy equation, d squared phi over d epsilon squared minus epsilon psi equals 0. Hence, we say psi now can be C1 A1 of psi plus C2 BI of psi. So we then have Python computation of Airy functions now. So if you take x to be 2.0, or I mean, you can make your x whatever you want it to be. So if x is 2.0, you can calculate AI, AIP, BI, BIP, Airy x now. So that AI prime, BI prime. So then we just print all of this and we have that. So what if we make it 1? Does it work? If x is 1, see what we get. We have all these values like this. So what if we make it 10? What do we get? We get all of this. So remember the other time when we did A1 of 10, we got something times 10 raised by minus 10. So this seems to align with our reality. So what if I make 100? I think it even goes further down. Yeah, the value becomes almost 0. For the decaying one, it's it's very, very close to 0. For the growing one, it's very, very big, very large, right? So that's how it all goes. So A1 decays, B1 grows seriously. Then comparing exact and asymptotic solutions now. So if you have AI exact and you have AI asymptotic based on approximations now, that's 1 over square root of pi, x raised by minus 1 over 4, exponent of minus 2x, like all the formulas we had the other time. So if you run all of this, see what we get. So they tend to align perfectly. So, and for AI of X, right, that's it's the decaying one. So it moves very fast towards 0. Then we have the Stokes phenomenon, which we also saw in the last video. Airy functions provide a classical example of the Stokes phenomenon. As one crosses certain rays in the complex plane, exponentially small terms suddenly appear. Then asymptotic expansions change form. This is fundamental in exponential asymptotics and complex analysis. That's the Stokes phenomenon, where when you move from region where x is where x is less than In the region where x is less than 0, you have oscillation. But once you leave that region, you then have maybe exponential growth or exponential decay. So that is the Stokes phenomenon. So in summary, we can now see that the Airy equation, which is y prime prime minus xy equals 0, if you like, y prime prime equals xy, has fundamental solutions, a1 of x, b1 of x. So for the behavior is such that when x is greater than 0, you have exponential behavior, whether growth or decay. When x is less than 0, so x is less than 0, you have oscillatory behavior. Right. So the importance is that Airy functions describe transition regions near turning points and provide uniform asymptotic approximations. So if you're talking about transition in regions like that, area equations provide a very nice way to visualize some of these things. So now we have practice problems, and as usual, I'm going to solve two of these practice problems. I'll be solving problems 8 and 12. So here you can see problems 1 to 4 clearly. Problems 1 to 4 verify directly that if y of x is this, then y of x satisfies y prime prime equals minus x y equals 0. Okay, I mean, all we just need to do here is we already have our y of x. So we just differentiate twice and them up, and everything should evaluate to 0 at the end of the day. Then use the power series method to compute the first the first 6 non-zero terms of the solution of this. Yeah. So you have problems 1 to 5, then 1 to 4, then 5 now, 5 to 10. Okay, we can't see 10 here. So let's say 5 to 9. So like I said, I'll be solving the run scan, this one, problem 8, which talks about the run scan. Compute the run scan, WAI of x, WBI of x. So we need to compute that run scan. I'm going to show that. Then we have 10 to 13. 10 to 13. The other problem I'll be solving is problem 12. Show that near a turning point, q of x not equal 0, the equation epsilon squared y prime prime equals q of xy reduces approximately to an Airy equation. We're going to show that also when we get there. Then you have 13 to 19, 13 to 19, 13 to 19. Then of course 20. Then 20 like this. So let's take the two problems we have to solve and see how we go. So start with problem 8. So problem 8 says compute the run scan, compute the run scan W of AI of x, BI of x. Okay, so of course the step 1 is to define the run scan. So definition of the run scan. So we know that for two functions, y1 of x and y2 of x, the run scan is W of y1 comma y2, which is determinant of y1, y2, y1 prime, y2 prime. So we can say then thus W of AI of x, BI of x is equal to, take the determinant of this now. So that's like y1, y2 prime, then minus y2, y1 prime. Okay, so in this case now, if our y1 is a1 of, so we can take y1 to be a1 of x, right? So, or let's just do it like this. We have y1, y2 prime minus y2, y1 prime. So like that. So we can, in a way, we can see y1 as a ai of x, and we see y2 as bi of x. So that means that y1 prime is y1 prime, right, is equal to ai prime of x, while y2 prime is bi prime of x. So in that case, then we have that the Wronskian would have to be y1, that's a I of x, y2 prime, that is b I prime of x, minus y2 now is b I of x, then y2 prime is, y1 prime rather, is a I prime of x. So we have that in that regard. So, but then, so we are doing that for the Airy equation, right? So we are going to use the Abel's identity. So the Airy equation is y prime prime minus xy equals 0, which can be written, which can be written, which can be written as y prime prime plus p of x y prime plus q of x y equals 0, with p of x equals 0 because we don't have this term, with p of x equals 0, and that's what makes it the Airy equation. So in that case, now we know that the Abel's identity Abel's identity states that w of x is equal to c e raised by minus integral p of x dx. And then since p of x is seen to be equal to 0, then we see that w of x is just the constant c, right? Just constant c. Therefore, the Wronskian is constant. The Wronskian is constant. So the next thing we need to do is to determine the constant. So we determine the constant. So, and to do that, we know that a standard property of Airy functions gives w into ai of x bi of x equals 1 over pi for all x. Okay, for all x. Okay, so the final answer is this. Final answer is just that the Wronskian of ai of x bi of x is equal to 1 over pi. So that goes. Now we move on to the next one. We talk about problem 12. So for problem 12, we want to show that near a turning point, q of x naught is equal to 0. The equation epsilon squared y prime prime equals q of x y reduces to an Airy equation. So an Airy equation. Okay, we need to show that. Yeah, there's the question again. Show that near a turning point, q of x not equals 0, the equation epsilon squared y prime prime equals q of xy reduces to an Airy equation. So let's go and deal with that now. So the solution now. First, we expand near the turning point. So suppose x naught is a simple turning point. Suppose x naught is a simple turning point. Meaning q of x naught is equal to 0. and q prime of x naught is not equal to 0. Okay, q prime of x naught is not equal to 0. So using using a Taylor using a Taylor expansion near x naught, we have q of x to be approximately q prime of x naught into x minus x naught. So we can define alpha to be q prime of x naught. Then the differential equation, the differential equation becomes the differential equation becomes epsilon squared y prime prime equals alpha into x minus x naught. Okay. And that, I mean, when we do the whole expansion here, so, first we should have q of x naught for starters. Then next we have this. So because q of x naught is taken to be 0, being a turning point, okay, so we are left with this particular expression. So alpha, if you take alpha to be q prime of x naught, then so epsilon squared y prime prime equals alpha into x minus x naught multiplied by y. So this is the expression we have now. So we have to now introduce a scaled variable. So we can define a scaled variable, define a scaled variable epsilon equals alpha raised by 1 over 3, epsilon raised by 2 over 3, multiplied by x minus x naught. Then we have that x minus x naught is equal to epsilon raised by 2 over 3 all over alpha raised by 1 over 3 multiplied by okay, there are two things here and we have to be careful not to confuse them. So here we have epsilon. This is some kind of special epsilon, while this one is just the regular one. Then down here we have x minus x naught, the regular epsilon here, and then this is the special one here. So there are two different ones. Let's take note of that. So with this now, we can talk about transforming the derivatives. So we transform the derivatives. We transform the derivatives using the chain rule, So that simply means that, so from here now, we are going to perform that transformation. So that simply means that ddx equals, so differentiating with respect to x now, ddx equals d psi dx d psi, that special one. So, and that is equal to that's equal to d psi dx. So d psi dx now would just be alpha raised by 1 over 3 epsilon, the regular epsilon raised by 2 over 3 multiplied by d psi. So it's like epsilon with the special wings. So the psi. Okay, so we have that first of all, and d squared, the x squared will just have to be, we differentiate again, d squared, the x squared will now have to be alpha raised by 2 over 3 all over epsilon raised by 4 over 3 d squared d psi squared, like that. So substituting into the equation, substituting into the equation, we then have epsilon squared. Is it epsilon or psi now? Yeah, epsilon squared. Yeah, we have epsilon squared y prime prime. So epsilon squared alpha raised by 2 over 3, epsilon raised by 4 over 3, d squared y, d psi squared. So epsilon and psi, we have to take notes, and that is equal to alpha into epsilon raised by 2 over 3, alpha raised by 1 over 3, then psi multiplied by y. So with that in place now, so if we simplify both sides, simplifying both sides, we then have alpha raised by 2 over 3, epsilon raised by 2 over 3, d squared y, d psi squared, all of this, d squared y, d psi squared, and that is equal to alpha raised by 2 over 3, epsilon raised by 3 over 2, epsilon raised by 3 over 2. There is epsilon raised by 2 over 3 here. So there's this epsilon 2 over 3. If we bring this over there, that's epsilon raised by 3 over 2. Okay, this is epsilon. So this epsilon here operates on this. So this is like, if you bring it down, that's epsilon raised by 4 over 3 minus 2. 2 is, yeah, so this can now go up as negative, as positive now. Because this will be e raised by 2 over 3 down here. So if you take it up, because this 2 is 6 over 3. So that's minus 2 over 3. So it goes up and the minus is gone. So we have alpha raised by 1 times this now. So it's like alpha raised by 1 minus 1 over 3. That's 2 over 3. Then epsilon raised by 3 over 2. Epsilon raised by 3 over 2. So it should be epsilon raised by 2 over 3. Yeah, nothing changes there. Epsilon raised by 2 over 3. Then we have psi, this psi here. Then we have y. Okay, so if we cancel the common factors, right? If we cancel the common factors, we just have this and this and this and this will go. So we have d squared y, d psi squared, equals psi, psi, psi. I always have issues with this. Psi y, which is as good as the Airy expression we know. Okay, that's that. So if we rearrange now, rearranging, we have that d squared y, d psi, d squared y, d psi squared minus psi y is equal to 0, which is precisely the Airy equation. The Airy equation. Okay. So we can then conclude that near a simple turning point, the equation epsilon squared y prime prime equals q of x y reduces locally to the Airy equation, to the Airy equation, y psi y psi psi minus psi y equals 0. Hence, hence, Airy functions, hence Airy functions provide the correct local approximation near turning points. Okay, and that's the end of this video about Airy equations. It's been such an eventful one, and we see how related it can be with the last video where we talked about asymptotic methods. So I'll flash the practice problems once more, and then this will be done with. So again, we have practice problems. You can see 1 to 5 here, I think. Yeah, this is 1 to 5. Uh I think I solved 8, right? Then yeah, we did 8 for Airy equations. So 6 to so this is now like 6 to 11. 6 to 11. And then we have 12. 12 to 18. And then up to 20 now. Let me know how helpful this is for you. If there's something else live in the trial, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, why not go ahead right now and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel by clicking on join. That gives you special privileges that you find out when you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.